Hello class, welcome to this continuation for the subtopics of chapter 2 on functions, and today we'll be still talking about inverse functions. What I want you to teach you about is a brief summary of all the stuff that we have seen about inverse functions, and then this last new idea, a strong requirement for a function f to have an inverse. The previous four numbers we have already talked about. The concept of the inverse function, the formal definition, what are one-to-one functions and many-to-one functions, and also how we can find the inverse function of a given function. Only with one group I that I am aware of, only with one group I have talked about this idea. So for most of you, this is going to be a new concept, a requirement for a function f to have an inverse function. So let's begin. We're going to cover this whole thing as quickly as we can. So number one, the concept. What is a concept? Just the concept of an inverse function. If we think of a function f as a machine, which we usually do, as a machine that does something, then its inverse function, represented by this symbol and read as f inverse, is a machine that undoes what f does. Okay, try to match this. F does and f inverse undoes what f does. What does this mean? It means this, guys. Imagine that you have this function f. I give you this function f, and you happen to observe that when you put any number into f, f will double such number. If you put the number 2, it's going to give you the number 4. If you put the 4, it gives you 8 as an output. And if you input the number 6, it gives you 12 as an output. So we understand what f is doing. F is basically multiplying by 2. That's the job. That's what this function f is doing. Okay? Fine, perfect. Imagine there is another function now. This function. And this function, and don't pay attention yet to this name. Okay, suppose this is not here. Suppose this function has the peculiarity or the feature that when you give it, when you give it all of these outputs given by f, for example, the number 4, this function will give you the number 2, which is the number with which f started with. Okay, you give it the number 4, it gives you the number 2, which is the same number as this. It gives you, if you give it the number 8, it gives you the number 4, which is the number that we started with. And if you give it the number 12, it gives you the number 6 in return, which is the same number with which we started this process. So you can see, you can observe, you can assess that this function basically is reverting or undoing what this function is doing. This function is multiplying by 2, and then this function is dividing by 2. If you give it 4, it divides by 2, and obviously it will give you 2. And the same for the rest of the numbers. So we call this function, this particular function, f inverse. Why inverse? Because it's inverting what f is doing. Okay, it's the reverse or the inverse process of what f is doing. That is the concept, guys. That is the concept of an inverse function. Now, some more examples of functions and their inverse functions in everyday life. We already talked about some ideas, right? For example, the idea of the sorry, the idea of the oven versus the fridge, right? As home appliances. What is an oven? It's something that is gonna raise the temperature of food. What is a fridge? It's an appliance that will lower the temperature of food, right? So these are inverse processes. You can think of the oven as the inverse function of the fridge, and you can also think of the fridge as the inverse function of the oven. Okay, and this type of behavior, guys, this type of let's say, uh, I mean, the way in which things behave in the universe uh, pretty much follows this idea. Okay, for many things that do processes, we can find another things that undo those processes. When you have this, when you have zoom out and a zoom in, these are inverse processes, right? These are inverse functions, one to the other. If you have any figure, any shape, and if you zoom out, this is the zoom out, then this function will take this shape and will make it tinier, right? Let's suppose it goes from here to here. This is the input, process, output. And then if you take this output and you apply the inverse function to the zoom out, which would be the zoom in, then the zoom in will give you, probably, I mean, with, if you apply it carefully, will give you the same as before. At least it has the possibility of give you the the first result, right? The original shape. So we shorten the size and then we enlarge the size. Inverse functions. The brain. I was telling one of your classmates that the brain is very peculiar because it can act as a function and also as its own inverse. This is a machine, guys. This is a machine. Think about this. Whenever your brain reads a word such as this tree, what is one of the first things that your brain does? It forms a mental picture, right, of such word. Okay, so the brain has as an input this word, which is pure symbols, right, and then it will form inside the visual representation of this word. Input, output, and the brain itself can have the other capability, right? When you give the brain the image of a tree, okay, the brain knows what word I'm sorry, what word corresponds to this particular image, right? So as you can see, it works in both ways. It can give you this output for this particular input, but it can also give you this output for this particular input. So it can reverse its own doings. It's pretty interesting. What is this? What is this machine? I told you that on World War II, there was a lot of mathematics involved in World War II. Why? Why do I say this? Well, because the Nazis were communicating among themselves through message coding. I mean, through messages, right? Messages. They want to transmit some message from some location to another location. Okay, a message. Some people here, and then hundreds and hundreds and hundreds of kilometers. There are some other Nazis here, some other Germans, and they need to transmit a message. Okay, how do they do this? By means of obviously radio signals. Okay, by radio signals they transmit messages. Okay, the problem is this: that the enemies of the Nazis or the Allies can intercept that message and read it and basically uh, discover what these guys were thinking of, right? What they were planning. So how do you solve this problem? What you do is you code, or well, encode. You encode the message. These people think up a message, they encode it through a machine, okay, and maybe something that looks like this. If this is the original message, after you encode this message through a machine, through a function, then maybe this original message is gonna look something like, I don't know, like CGHITRTSAB, something like this, right? So this is the original message, this is the encoded message, and then they can send that message to the other party, to the other comrades, and these people will have to decode that message, and they can do it because they have the key. They have the way to do it. They understand how to encode and decode the messages. And by doing this process, guys, of encoding and decoding consistently, these two parties, which are comrades or son del mismo bando, they can be communicating without any interception from enemy parties. You see? So this encoding and decoding are inverse functions, right? And then uh, luckily for everybody, I guess, there was a mathematician working for these guys, for the Allies, for the for the for the British. There was a mathematician that could know how this machine worked. This was the machine used by the Germans in order to encode and decode. He could, using pure mathematics, just mathematics, he could find how this thing worked, and basically it broke the code of the Germans, and that's basically how they won the World War II. Okay, very interesting stuff. So yeah, I mean the concept of a function and the inverse function is everywhere, guys. It's everywhere. It's just get to think about it, and you will find functions and their inverse in many places. Okay, now what is the formal definition of an inverse function? Now that we know the concept, what is the formal definition? Given a function f, its inverse, represented by the symbol, like I already told you, this is the symbol representing the inverse of f. How do we read this? F inverse. Not f to the minus 1, f inverse. That's how we read it. And this function is the function such that fulfills this equation. And I know it looks kind of creepy or kind of scary, but it's not. It's not. What is this telling you? It tells you this. If you evaluate f inverse in f of x, you will get x. And if you don't understand this by means of the equation, I just want you to go back to what we talked about in here. Okay, f is the inverse process of f. When f inverse takes the output of f, such as the number 4, it will revert back. It will give you back the number with which f started. Input, output, and then if we have this output into f inverse, the result that f inverse will give me is the original input with which we started. Now let's translate this idea here in order to understand this equation. Okay, well, here is f, here is f inverse. What is f doing? F is doing this. You give it the number x, and f will give you f of x, because that's what f does. This is the input, this is the output, right? By now you should understand this symbol as the output of f. Now if you give this particular output into f inverse, what is f inverse gonna do? It should give you the same input with which f started. You see? So in other words, when you evaluate f inverse in this number, in this value, when you go like this, let me evaluate f inverse in this particular value. In this particular value, we should have that the result should be x. That's all this is telling you guys. You see, when you see an equation like this, try to interpret what it's meaning in terms of visuals, graphs, and some other things, because it's very easy to get lost by just paying attention to the equations themselves. Next, one-to-one functions and many-to-one functions and the vertical line test. F is one-to-one, or f is a one-to-one function if every output of f corresponds to only one input of f. And this is an example. Okay, if you pick any output that is part of f, this output, and you go look for its corresponding input, you will only find one. You see, for this output, only one input corresponds. For this output, I'm sorry, for this output, only this input corresponds. Output, just one input, and the same for all the rest. So this is a one-to-one function. And this other type of function, something like that looks like this, something whose graph looks like this is what we know as a many-to-one function. What is the definition of a many-to-one function? F is many-to-one if at least one output of F corresponds to many inputs of F. For example, if I choose in here in this axis for the outputs, let me choose the number 4. This is one output. We can see that this output corresponds to many inputs. And by many, I mean more than one, which is the number 2 and also the number -2. You see, if I can do this with at least one output for F, then this is many to one. Only one of this is all I need to classify it as many to one. Okay, in this case though, the same is going to happen for any other output that I choose. If I choose this output, this corresponds to 2 inputs, and the same for any other output. Same with here, right? If you do the same exercise that I did in here, you will find the same. For each output in here, you will only find one input. Output, one input. And in here, you may find at least one output. Let's choose this, -6. And if you go look for the corresponding inputs for this particular output, you will find many. What does many mean? More than one. Let's do it. I cannot draw very well. There is one. There is another input and another input. These 3 inputs, whatever their values are, they go into this output. You see, so this is many to one. How do we find the inverse function of a given function f? If I give you this, given f of x equals to x, find f inverse. All you need to do is basically the following. Just to remind you very quickly, this is the function. What I want you to do is change the output for y. I mean, you can do the whole process with f of x, but it's much simpler if you change it for y. Okay, then isolate the x, isolate the input variable, put it on the left. Okay, and at this moment, when you have the x variable or the input variable isolated, at this moment change this for f inverse of x and change the y for x. Okay, and this is gonna be the f inverse, the inverse function for this particular function, which makes sense, right? If f is a function that multiplies by 2, right, f inverse should be the function that divides over 2, divides its input over 2, and therefore we can readily and clearly see that these two are inverse functions. They're doing the opposite, multiplication by 2, division by 2, and the same for the rest. I'm not gonna waste time on this. Okay, here comes the tricky part of this lesson. For many of you, this is gonna be new. Here we go. We have a strong requirement, guys, a strong requirement for a function to have an inverse. Not all functions have inverse. I'm going to repeat that again. Not all functions have inverse. Okay, why? Because of this. Let's read first this little text. A function f only has an inverse if and only if f is 1 to 1. That is a requirement, guys. F will have an inverse only in the case that f is 1 to 1. F must be 1 to 1 in order to have an inverse. If f is many to 1, then, formally speaking, it cannot have an inverse. Okay, so 1 to 1, they have an inverse. Many to 1, they do not have an inverse. And let me explain to you why. Let me go back here. Okay, this is the tricky part of today's lesson, I suppose. Here it goes. Don't pay attention to anything in this slide other than this, guys. Just I want your whole mind to be on this graph. Let me ask you this. Is this a function? Yes. Yes, it is. Because it passes the vertical line test. Perfect. This is a function. What type of function is this? Is it 1 to 1 or many to 1? By now you should agree that this is many to 1. Many to 1. Let me backtrack a little bit. I'm going to explain to you first the idea by using this. Okay, so I'm going to go here in a moment. Just pay attention for the moment here. This is a function that is 1 to 1. Okay. Okay. Why do I tell you that these ones do have an inverse? Okay, you can actually calculate the inverse, or you can find the inverse function to this particular function f. Why? Because of this. You need to understand f, guys, in the following way. F is a machine for which you give it an input and f gives you an output. In this case, if you give f the value of 2, f will give you the value 3 as an output. If you give it the value 1, which is this one, if you give it an input of 1, it gives you the value of 2 as an output. You see? Input, corresponding output, input, corresponding output. Okay? That's what f is doing. Now think of f inverse now. Think of f inverse. If this is f, it's a function that gives you these outputs in response to these inputs, then think of what f inverse does. What f inverse should be doing is the opposite. When you give f inverse the value of 3, it should give you the value 2 as an output, right? Like it goes from here to here. That's what f inverse does. If f goes from here to here and from here to here, f inverse goes in reverse. It goes from 3 to 2, and it goes from 2 into 1. In other words, if you input the number 2, it gives you the output 1. You see? F goes in this direction. F inverse goes in the opposite direction. Okay? Now, let's see why, now that we have understood that, let's see why this cannot have an inverse. These type of functions cannot have an inverse. No inverse. No inverse. By making allusion to the same type of exercise that we did in here, like going in some direction and then in the opposite. Okay, here it goes. Let's call also this function f. Let's call it f. Let me erase this. Let's call this function, let's call it f. Perfect. What is f doing? For example, f, if you give it the value of 2 as an input, f will give you the value of 4 as an output. Perfect. Perfect. Nice. Also, f, if you give it the number minus 2 as an input, it will give you also the number 4 as an output. Okay? And that's going to cause a problem, guys. This type of behavior, the fact that we have two inputs going into the same output, will cause a problem if we try to calculate an inverse function for f. We won't be able to. Why? Because of this. F inverse should be doing the opposite, right? It should go from here to it should take this output and give you the input that you gave to f. The problem is this: how is f inverse gonna decide on which one? Like, if you give f inverse the number 4, how is f inverse gonna decide on what output it should give you, the number 2 or the number -2? Because f inverse is a function, right? And if you put any input into f inverse, it should give you only one output. You see? And if you put the number 4 into f inverse, first of all, it cannot give you both. It cannot give you both the 2 and the -2 as responses, because then this wouldn't be a function, right? So now that you understood that, then let's face the other problem. If you want just to pick one of these two as a response of f inverse, how do you decide? For this, when you input this into f inverse, which of these is going to appear as a response at the end of f inverse? You see? So that's the problem. That's why we cannot calculate inverse functions when your original function is many to one, because it presents that particular problem. Okay? Because of that problem. Because there are two inputs that go into one output, and when you want to reverse the process, you won't be able to. Okay? Para este output habría dos posibilidades, y eso hace que no pueda existir una f inversa para este tipo de función. Aquí lo voy a parar. Ya fue mucho video. Si quieren seguimos hablando de esta idea para que la entiendan bien. ¿Por qué este requisito de que sea la función 1 a 1 es indispensable para poder sacar una función inversa? Sale, chicos.